Why is it that when we multiply out a binomial, we get this interesting pattern of coefficients? So let's think about multiplying a plus b times a plus b times a plus b times a plus b, but I've color-coded them so that each of the binomials has a different color, so we can see the different pathways that we get to multiplying these all out. So think about this. I'm going to be multiplying a plus b times another a plus b. When I do that, I could multiply a times a, black a times blue a, or I could multiply black a times blue b. Or I could multiply black b times blue a, or black b times blue b. So that would give me 4 different multiplications, just multiplying those two together. And you know that when you multiply two binomials, you get 4 different multiplications. That's what the letters F-O-I-L stand for in FOIL. But I could also then keep going with this. Once I've done the black ones times the blue ones, then the blue ones are going to be multiplied times the red ones. So the a could go times the red a and the red b, the blue b times the red a and the blue b. Okay. Now the reason I'm doing it again here and here is because this one started with the black a, but this branch starts with the black b. So those are all different multiplications that I get. Then finally, I take the red ones times the green ones, and so that branches me out again. So what I end up with is 16 different branched multiplications. I could end up with a times a times a times a times a times a times b, a times a times b times a times b times b, etc. And what I'm ending up doing here then is I'm seeing how many times that I get each pattern of coefficients. So there's only one way to get a times a times a times a. And there's only one way to get b times b times b times b, b to the 4th down here. So that's why our first and last coefficients are 1. How many ways are there to get the second term, a cubed b? Well, I've got a b here. I've got a b a, that's another a cubed b. And then down here I have a b a. And then over here I have b a. So there's actually, the ones that are circled in red, there's 4 different ways to get 3 a's and a b when we multiply through these branches. Now how many ways are there to get 2 a's and 2 b's when we multiply? So if we count all those ways, here's an AABB, here's an ABAB, and so forth. It turns out there's 6 different branches that give me 2 a's and 2 b's. 4 different branches that give me 1 a and 3 b's. So it's just a tree diagram showing the different paths I can go through and multiply. This is just showing the row of the Pascal's triangle, how 1 plus 3 gives me 4, and 3 plus 3 gives me 6, and so forth. And you can see it actually in the 2 different branches. Here I have 3a cubed b's on this side of this branch of the multiplication, and 1 over here. So there's the 3 plus 1. There's the 3 plus 1 right here. Here I have a 1 plus 3 for the 4ab. So you can think of that as the 1 plus 3. And then I have 3 different ways to get a squared b, that's the blue ones, on each branch, and that's the 3 plus 3 here. So there's all kinds of interesting connections and patterns which shows the reason why these patterns exist in math.